Welcome to Radio System Design, Module 10, Nonlinearity, Gain Compression. So in this module we're going to talk about one basic concept, and that is gain compression, and in particular the 1 dB compression point. All right, let's examine first the input-output power relationship of a system. And before we talk about this, I just want to go over what an amplifier looks like in a dB plot. So let's assume I have an amplifier with a gain G. Okay? If I put X in dB, I would get X out plus G. Now we're assuming here that G is in dB and X is in dBm. And if you're not sure why that is, well, in the linear domain, right, it would be the input signal times the small signal gain, right? But if we take if we just take the log of that, you know we would get the log of X plus the log of G, right? And I've ignored the 10 that goes out in front of here, right? So you can see how multiplying in the linear domain, we're just going to add in the log domain, and that's why we use the log domain. So now if I come in with X plus Y, what's the output going to be? Well, it's simply going to be X plus Y plus G. And what we notice is that the output power, or the output power of the amplifier, is P in plus G. This is P in. Okay? So you can see that there's a linear relationship between P in and P out. And most notably, the prefactor here is simply 1. That means if I plot P out, and this is in dBm, P in dBm, what I'm going to do is have a straight line with a slope of 1 with an offset equal to G. So my slope will be 1, right? That's what I have here. P in goes up by 1, P out goes by 1, and this offset is simply my G. So any linear amplifier that has a power gain of G is just going to have an offset, but its slope is going to be 1. Okay? This is just an important point as we go into the next slides, because you'll see that we'll be assuming different slopes for different components, and as we do the Taylor expansion, we'll also see how this affects the 1 dB compression point. All right, so let's go take another look at a specific example. So I've shown you here before. Here's your input X, and our output is X plus G. I know it intersects here at 0, but let's just imagine that this is 0 and it has an offset of G here. Okay? And then as I put in my X plus Y, all it does is it moves up, as I showed on the previous slide. And the question is, what is the slope? We know that answer. It's simply 1. But at some point, as the power increases, the amplifier stops being linear. And we say that the output starts to compress because typically the gain reduces. We'll talk later, it could expand, but almost most systems, particularly if you're reaching a maximum voltage or a maximum power output, you tend to have it compress, meaning the gain gets less. And so in this region, we've got a nice linear power gain. Here, we're starting to compress and starting to get out of that linear region. And so we particularly take note when the output power drops 1 dB less than the expected value. So when this point is 1 dB below, that's sort of a metric where we say, at this input power, we're really leaving the linear range. And we call this point the 1 dB compression point. And it can be expressed as an input or an output. And what do I mean by that is I can say the input 1 dB point, compression point, is a certain value, and the output is a certain value. And those two are related. So let's talk a little bit about gain of an amplifier so that we can calculate where this 1 dB point occurs. So we're back to our old nonlinear amplifier where I've got an input, and this is cosine omega t. And on the output, I have expanded it in a Taylor series. Now, I just want to point out here that you should check right away, because this is a signal, and this is a voltage, we're dealing with the voltage transfer function. And we need to remember in the previous slides we've been always dealing with the power transfer function. And that's not a problem. You just need to remember it because remember power is going to be 10 log and a voltage is going to be 20 log when we go into the dB scale. And we want to take particular look at, in this case, what happens to the main signal cosine omega t, and specifically what happens to its coefficients. So we're going to focus on the fundamental cosine omega t, and we're going to look at the ratio between an and the coefficient of cosine omega t at the output. And we're going to define the gain, and this is only valid for cosine of omega t, just for this one frequency, as the ratio of the output to the input. I can simplify that, and I can actually simplify that one more step. And I'm going to do this for convenience later on. Okay, where I've just pulled this alpha 1 out there. Okay, for small input levels, alpha 1, the gain is alpha 1 and it's linear, and that's because typically alpha 3 is small, and if the input is small, the input squared is very small, and so we're left with the gain as just being alpha 1. As the input gets larger, depending upon the sound of alpha 1 and alpha 2, the gain can actually expand, and that means it increases, or as we said before, it can compress. And most electronic systems have a compressive behavior, but that's not always the case. So eventually, as we noted before, as the power gets to a level, we get to a 1 dB compression point. And I want you to notice what's changed here is we've gone from the input power and the output power to talking in terms of the voltage. So now we've gone to 20 log of A, whereas the power would have been 10 log of the power gain. And we're going to try to calculate where this 1 dB compression point would be. All right, so let's take a look at this. If we have P out equals P in plus G, that's this linear line here. And if we want to find the 1 dB compression point, we just subtract 1. So we want to find the point where the P out is 1 dB below this. So if you remember, the gain is simply alpha 1 plus 3/4 alpha 3. Actually, we rewrote that, and I'll do that to make it simpler. Alpha 1, 1 plus 3/4 alpha 3 over alpha 1 times A in squared. That is our voltage gain, if you remember, and we're going to want that to find out when it is equal in the power domain to G minus 1. Well, if I take 20 log of this, I'm going to get 20 log of alpha 1 plus 20 log of I'm going to get 20 log of 1 plus 3/4 alpha 3 over alpha 1 A in squared, right? Remember, this is in the voltage domain, and this is in the dBm domain, right? And so I'm just taking the 20 log of V to get me into the power domain. And now what I can do is I can compare this with what I want, and I can see that this right here is G, right? Because alpha 1 is the linear gain. And so I can simply set then 20 log of 1 plus 3/4 alpha 3 over alpha 1 A in squared equals minus 1. Okay? And so let's just take that out. I'm going to end up with 1 plus 3/4 alpha 3 alpha 1 A in squared equals 10 to the minus 1 over 20. and then I can subtract 1. I can get rid of this on this side, and then I can multiply by, I'll just do this here, 4 alpha 1 over 3 alpha 3 times 10 to the minus 1/20th minus 1. And I take the square root of that. And that is going to give me the voltage amplitude where my 1 dB compression point has. And you can see we can write it simply in terms of alpha 1 and alpha 3. So if you're given the Taylor expansion of the voltage, right, voltage expression, you can calculate where the voltage would be, and the power would be related to that voltage. And if you do the math, you can calculate it out, and it then turns out that the amplitude input for 1 dB compression is the square root of 0.145 times alpha 1 over alpha 3. All right, and that'll be an easy way for you to calculate this in your homeworks and in your future life as RF designers. All right, that's it for gain compression and our definition and calculation of the 1 dB compression point.